matrices today. I found like these first initial sections are quite long in terms of like the number of slides that need to be covered. So it's kind of a brisk pace, I would say. For like the subsequent sections, I'm going to have more time for like asking questions and like allowing you to actually interact. So this is like, it's like one final day of me kind of going through things relatively quickly just to get all the prerequisite material out of the way. So we're focusing on matrices today. Matrices are kind of like vectors, except they're all grown up in a sense. They can encode more information. In a sense, like vectors are kind of just like rows or columns of a matrix. So you either have like one row or one column for a vector, but for a matrix, you can have multiple rows and multiple columns. So when I talk about the size of a matrix, the size of a matrix tells how many rows and columns it's going to have. Where if we have an M by N matrix, it means we're going to have a rectangular array of numbers where we have M rows and then N columns. So the first number, M, denotes the number of rows you have, and then N denotes the number of columns. So a 3 by 3 matrix is just going to be a collection of 9 numbers where you have 3 rows. So this is row 1, this 1, 0, 0. Row 2 is 0, 1, 0. And then row 3 is 0, 0, 1. So these are the 3 rows right here. And then you have 3 columns, 1, 0, 0, 0, 1, 0, and then 0, 0, 1. So this is what's known as a square matrix because you have the same number of rows as you do columns. And then you can have more rectangular matrices. So something of the form of a 2 by 4 matrix will look like this. We have 2 rows, and then you have 4 columns. So rows are horizontal, columns are vertical. And then a 3 by 2 matrix would look like this. So that's the size of a matrix. You have to be able to recognize or be able to, like, it says like make like a 5 by 2 matrix. You have to know what that's going to look like. 5 rows and 2 columns of numbers. And so there's a number of different ways in which you can talk about matrices or write about matrices. So I dedicated a slide to matrix notation. And so the object or the number in row I and column J of a matrix is going to be called the ij element, or sometimes I'll call it the ijth entry of your matrix. And sometimes it's denoted by this like capital A, ij. So we're looking at matrix A, and then we're looking at the ijth element of that matrix. And a common way, not just for this class or this book, but throughout like all of math, to denote a matrix is just by writing it in the following way. So it's really saying this matrix A is a collection of these entries aij, where you have like this double index I corresponding to the row, and J corresponding to the column. So this is like the ijth entry or element of your matrix. And so the distinguishing factor, if I just had the aij without the brackets, this would be the ijth entry of your matrix, but with the bracket, it's saying that this is the entire matrix. This is useful when you're writing out equations or operations between matrices, and that you can have an idea of what the general entry or what form the general entry is going to take. Okay, and then some more notation that's going to be common throughout this class. We can think of the ith row as an M vector. What I mean by an M vector is it's going to be a vector with M elements or entries inside of it. So this is an example of the ith row of an M by N matrix. Or I guess this would be an N by M matrix. Sorry, I should have, I messed this up a little bit. But the thing to keep note of is the row is going to be constant for this matrix, right? The row stays the same, but the column is what changes. So this is the first column, like the ith entry in the first column, ith entry in the second column, ith entry in the mth column. And then similarly, the jth column of your matrix you can view as an n vector. So it's kind of just taking what we were doing before, except like rotating it 90 degrees. So this is the first row in the jth column, second row in the jth column, and then nth row in the jth column. So you can write it as this kind of vector as well. Like these are two equivalent ways of writing the exact same thing. So if all the components are only real numbers, then the row vector is in Rm, and then the column vector is going to be in Rn. Okay, and then continuing, we'll start talking about operations between two different matrices. So just like vectors, we say two matrices are going to be equal to one another if their entries are the exact same. So if we have that Aij is equal to Bij for every single I and every single j, then we say the matrices are going to be equal to one another. And then a common way of if you have two matrices, you can make another matrix just by adding the two of them together. And this is going to be done entry by entry. So if we have two matrices A and B and we add them together, the ijth entry of the new matrix is just going to be the sum of the ijth entry of A plus the ijth entry of B. And so I'll look at an example on the next slide. So for this next slide, it wants us to add two matrices together. And so again, you just do this entry by entry. And again, you can only add matrices together if they have the same dimensions, just by the definition. So if we wanted to add these two entries or like these two matrices together, it'll be entry 1, 1 of the first matrix plus entry 1, 1 of the second matrix. So it's going to be 1 plus minus 1. That'll be the first entry. And then you do 2 plus 5 for entry 1, 2. So first row, second column. Then you have minus 3 plus e to the minus 3x. And then so on. Like, I'm not going to go and like explain every single one. So the next, well, I'll write it out like this though. So the next one would be 4 plus 8. Then you have sine of x plus 9. And then the last entry would be 0 plus 0. So you're going to get another 2 by 3 matrix. 1 plus minus 1 is equal to 0. 2 plus 5 is equal to 7. We'll keep this as minus 3 plus e to the minus 3x. 4 plus 8 is equal to 12. We'll keep this as sine of x plus 9. And then 0 plus 0 is equal to 0. So you just add the corresponding entries together to get the new entry, and they get the sum of the matrices. Are there any questions about how I got this matrix? Okay, so matrix addition is the more intuitive operation between two matrices. The main focus is going to be multiplication of matrices. That's going to be a lot more useful in terms of the applications one has for matrices. And so there's, I guess, two main ways we're going to be thinking about matrix multiplication in this class. One is in terms of linear combinations of column vectors, and the other is in terms of dot products between rows and columns of your two matrices. So I'll go through and look at the applications of both of these ideas of matrix multiplication. They'll give you the same matrix at the end of the day, just different ways of viewing them. So first we'll look at matrix multiplication as linear multiplication or linear combination of columns. So we're going to assume that A is an m by n matrix, and we're going to have n columns denoted by A1 up until AN. So A1 and up to AN, these aren't numbers. Again, these are just going to be, these are the column vectors. So these are going to be m vectors, right? They're going to be vectors with m elements inside of them because they're columns. And we'll look at an example later on to make this more clear. And then we're going to assume that this bold X is a vector in Rn. Then the product of A and X, so this matrix A and this vector X is going to be denoted by AX, so like A times X. And it's going to be the linear combination of the columns of A using the corresponding entries in X as weights. So what I mean by this is if we have that A is this matrix right here. So again, A1 up until AN, these are column vectors with m elements in them. And then this is our X. If we do A times X, like i.e. multiplying these two things together, the corresponding result is it's going to be a linear combination of these column vectors. So we have A1, A2, AN, where the weights or scalars that we're multiplying to these column vectors are determined by the entries of your X vector, your vector X. So the corresponding weight of A1 is going to be X1. Corresponding weight to A2 is going to be X2, which is the one beneath X1. And then the weight slash scalar for AN is going to be this XN right here. And so you should really be thinking that this is a dot product, right? This is the dot product of A with X, right? It's A1 times X1 plus A2 times X2 all the way up to XN times AN. You can also think this is a dot product of the column vectors of A with this N vector X right here. And so we'll look through a specific example. This isn't the most interesting example in that I kind of just give you, like, this is just going to be a dot product of two vectors, but we'll look at more interesting examples later on. And so if we wanted to multiply these two matrices together, is this going to be the dot product of 401 with 437? And then you can also think it's going to be a linear combination of 4 by 4 plus 3 times 0 plus 7 times 1. So you can write it like 4 times 4 plus 0 times 3 plus 1 times 7. And it's just going to end up giving you a number because we're really just taking a dot product in this scenario. And so this is going to be equal to 23. I will say though, like in this scenario, the matrix product is going to end up being a number. But if you have larger matrices, usually if you multiply matrices together, you end up getting another matrix of a specific size that I'll talk about later on. Okay, any questions about matrix multiplication so far? Okay. And then I have a couple of slides where I work out the dot product. Okay, so we'll just keep on continuing. Just like vectors, we can look at multiplication by a scalar. So a scalar, again, you should just be thinking of as a real number. It can be like 2 or 3 or something along those lines. And scalar multiplication of a matrix is the exact same as it is for a vector. All you do is you just take every single element inside of A, and then you just multiply it by your scalar. So in this case, our scalar is alpha. So if you multiply alpha by A, you just multiply every entry of your matrix by alpha. So that should be pretty intuitive. Okay, so here's the more formal way. So before I was talking about matrix multiplication as a linear combination of your column vectors. This is kind of the more common way of writing out matrix multiplication. So a product AB of matrices A and B is defined first off only if the number of columns of A equals the number of rows of B. And then what the ijth entry of your new matrix is going to end up being is it's going to be the sum that we have here. So at least in this class, you're not going to have to work really hard or understand this sum too hard. But what it's really saying is that this is going to be the new ijth entry of your matrix is going to be a dot product of the ith row of your first matrix by the jth column of your second matrix. So the I and the j in this sum remain constant. So this is like the ith row of A, jth row or jth column of B. And then what's going to be changing is which entry you're considering in the ith row and what entry you're considering in the jth column of B. It'll be more clear after I work through an example. Like you shouldn't look at this and be like, oh, this makes, I understand now. I know how to do it. Maybe you do. But it's like more practical to work through examples to understand what's going on. And so this is a really important note. I should have said like really important note here. Again, as I said before, in this, in order for you to be able to multiply two matrices together, the columns of the first matrix has to be equal to the number of rows of your second matrix. So these two numbers have to be the same. And then if you multiply two matrices A and B with one another, the product matrix AB is going to be an M by M matrix. So you take the number of rows in your first matrix and the number of columns in your second, and that will determine the size of your new matrix A times B. So it's going to be N by M now. So the N comes from here, the M comes from here. That's going to be important. It's like a good way of like checking to see if what you're doing is correct, right? And I think I go through, so I'll go through an example here using the equation I was talking about in the previous slide. So if I want to determine the product of this matrix right here, first off, let's just take note of the size of the matrices that we have. So this first matrix, this is a 2 by 3 matrix because we have 2 rows and 3 columns. And then this is going to be a 3 by 1 matrix. And so we should have that the matrix we get after matrix multiplication should end up being a 2 by 1 matrix, because we have 2 rows in the first matrix and then we have 1 column in the second matrix. So it should end up being a 2 by 1 matrix. And so how you determine what this 2 by 1 matrix is going to be is the first, like the 1, 1 entry of this new matrix is going to be the dot product of the first row of your first matrix with the first column of your second matrix. So this is going to be, so the dot product is going to be 1 times 4 plus 2 times 3 plus minus 1 times 7. So that was the dot product of this first row by this column. And then the second entry, so this is the 2, 1 entry, is going to be the second row of your first matrix dotted with the first column of your second. So this is going to be 0 times 4 plus minus 5 times 3 plus 3 times 7. And so you'll get a 2 by 1 matrix. This is going to be equal to 4 plus 6 minus 7. This is going to be equal to 0 minus 15 plus 21. So this is equal to 6. 6. Oh wait, what am I thinking? I don't know how to add. That's, I think I don't know what I was doing. So this is 3, not 6. Right, 4 plus 6 minus 7 is equal to 3. And then this is equal to 6. Okay, any questions about this example? Okay, and we'll look at more sophisticated examples later on in this class. Yeah, 3, 6, cool. Let's see, what am I saying here? Oh yeah, so this is like the exact same. I think I just added this note from going from the previous slide to this slide. I guess like, oh, okay. Yeah, so like the thing to note here, this is important actually. I think like everything you've worked over through like high school or maybe like the classes you've seen in college so far, you can always change the order of operations for your product. This isn't going to be true for matrices. So if you have 2 matrices, A and B, if you multiply A and B with one another, there's no guarantee that it's going to end up being equal to B times A. So you can't switch the order of matrix multiplication and assume that you're going to end up getting the same matrix over again. There are some scenarios where it ends up being true, like if B is a like diagonal matrix multiplied by a scalar. But in pretty much any situation, like it's not going to end up holding true. So I think I go through an example here next. Oh, maybe later. Yeah, we'll do have like a demonstration showing that A times B is not necessarily equal to B times A later on. Okay, so this is the other approach to matrix multiplication that I kind of briefly went over earlier in this presentation. This is kind of the interpretation of viewing matrix multiplication as a linear combination of your column vectors. So under that like that other interpretation of what's going on, if we wanted to compute this matrix product using this method I was talking about earlier, where again, like this is really just linear combinations of your column vectors, A1, A2, and then these are your weights. If you wanted to compute this specific example with this approach, it would be done in the following way. So instead of doing like the dot product of the row with like 4, 3, 7, we can instead interpret it in the following way using this equation where x1 is equal to 4 and a1 is equal to the first column of your matrix. So this is going to be 1, 0. And then you can keep on going. So x2 is equal to 3. And then a2 is equal to 2 minus 5. And then x3 is equal to 7. And then this third column is equal to minus 1, 3. And so if you consider the linear combination of these vectors, you would end up getting the exact same answer we had before. So it's going to end up being equal to 3, 6. So there are different approaches to matrix multiplication, but they give you the same result at the end of the day. And so all it was doing this matrix multiplication, except using this interpretation of writing matrix multiplication as a linear combination of column vectors. So either way works. There are benefits, like it depends on the situation or the question that you're asked. It's going to determine which interpretation of matrix multiplication you're going to be using. But you should know both interpretations or approaches. Any questions about this? Okay. What do we have next? Okay, so I think that's going through matrix multiplication, at least all you need to know thus far. After talking about this theorem, we're going to start talking about like solving systems of linear equations using matrix multiplication and what it means to have invertible matrices. But before doing that, just some basic algebraic properties of matrices in terms of like how their sums interact with multiplication and how scalar multiplication works with respect to products and all that good stuff. So if we have 3 matrices, A, B, and C, we have the following properties. So unlike multiplication, if you add 2 matrices with one another, it's going to be commutative, meaning you can switch the order in which you add the matrices with one another. So A plus B is equal to B plus A. You can distribute matrices, matrix products over sums. So if you have B plus C in parentheses, you can distribute A over the sum. So this is the same as A times B plus A times C, just like with real numbers. So that should be pretty familiar. And then similarly, I have an extra parentheses here. If you do A plus B times C, this is going to be A times C plus B times C. So whether it be left or right multiplication, it still distributes over the sum. Matrix multiplication is associative, meaning it doesn't matter in what order you have the parentheses. And again, there's like one too many parentheses. And then with scalar multiplication, if you do alpha times the product of A times B, it's the same as first multiplying A by alpha. And that ends up being the same as doing like alpha times B and then multiplying by A. So it doesn't matter in which order you multiply the scalar. It all works out. It's all good. And then we saw earlier that matrix multiplication is generally not commutative. And what I mean, just to clarify, I don't know if people have seen the word commutative or not. We may have situations where A times B is not equal to B times C. I think this is where I actually go through an example. So just as a simple illustration to show that A times B may not be equal to B times A is the following. So the first thing I want to note, maybe I'll do this a couple of times here in the beginning of the semester. A is a 2 by 2 matrix, and then B is a 2 by 2 matrix. We have 2 rows and 2 columns. So we should have that AB is going to be a 2 by 2 matrix as well. And so if we want to multiply these 2 matrices with one another, so this is 1, 0, 2, 4, times -2 times 6, and then 1, 3. Oh, I should label this. So this is AB, or A times B. So the first entry of our new matrix is going to be the dot product of 1, 0 with minus 2, 1. So it's going to be minus 2 plus 0. The second entry in the first row is going to be 1, 0, dotted with 6, 3. So it's going to be 1 times 6 plus 0 times 3. So that's going to be 6 plus 0. And so this is the new first row. Again, the first entry was the dot product of the first row and the first column. The second entry is the dot product of the first row with the second column. And then the entry 2, 1 in our new matrix is going to be the dot product of the second row with the first column. So that's going to be 2 times minus 2, which is minus 4, plus 4 times 1, which is equal to 4. And then the 2, 2 entry in our new matrix is going to be the dot product of the second row with the second column. So it's going to be 2 times 6, which is going to be 12, plus 4 times 3, which is also equal to 12. So we get a new 2 by 2 matrix. It's going to be minus 2, 6, 0, 24. So that's A times B. Before I move on, are there any questions about how I computed A times B? Okay, and then we'll look at what happens when we do B times A. So if you do B times A, you just switch the order in which you're multiplying the matrices. So you have minus 2, 6 in the first row, 1, 3 in the second row, and then A is 1, 0, 2, 4. I'm going to go through this computation a little quicker due to time. So this is going to end up being minus 2 times 1 plus 6 times 12. So that's going to be equal to 10. The next entry is going to be minus 2 times 0 plus 6 times 4, which is going to be equal to 24. This next entry is going to be 1, 3 dotted with 1, 2. So that's going to be 1 plus 6, which is equal to 7. And then the last entry is going to be 1, 3 dotted with 0, 4. So it's going to be 0 plus 12, which is equal to 12. And so you can see, like, these matrices really aren't even close to being equal to one another, right? And there's like no reason to really expect them to be equal to one another. Once you switch the order, like it's like a completely different equation in a sense, and that like you're changing which vectors you're dotting with one another. So you should expect like a wild variance. Like there's no reason to expect them to be the same. So the main conclusion I'm getting at here is that AB is not equal to BA. So in general, you can't switch the order of matrix multiplication. Okay, any questions here? Okay. Next, okay, so this is kind of where, I guess this is a preview of section 2.1, or really chapter 2. We're gonna spend a lot of time in terms of thinking about solving linear equations using matrices. And it's actually why they were first introduced in the first place, or matrices were first introduced, is to solve these linear systems of linear equations. So for the remainder of this class, we're going to be assuming that U, V, and W are as follows. So they're all 3 by 1 matrix, or 3 by 1 vectors. And so what we're going to be interested in is linear combinations of these vectors, and we want to be able to interpret these linear combinations of vectors in terms of matrix multiplication. And so this is why it's useful to interpret matrix multiplication in terms of linear combinations of column vectors. All right, so if we have an arbitrary linear combination of the vectors u, v, and w, where we have that x1, x2, and x3 are the weights associated to the 3 vectors, you can rewrite it in the following way, just by using what we defined for u, v, and w. So this is really x1 times this vector plus x2 times this vector plus x3 times this vector. So if you add them all up, you're going to end up getting a 3 by 1 matrix, right? So this is going to be like you have an x1 associated to this. So this is where this x1 comes from. You have 2 times x2. That's where this 2x2 comes from. And then you have x3 times 1. So that's where this x3 comes from. Then similarly, we have x2 times 1 shows up here, plus x3 times 1 shows up here. And then x1 only shows up in the third component of a vector in the first one. So this is x1 times 1 gives you this x1 right here. And so from that alternate approach to matrix multiplication I was discussing, where we're interpreting matrix multiplication as a linear combination of the column vectors of a matrix, you can rewrite this linear combination as the following matrix product. Right, so you can rewrite this linear combination as a product of matrix A times X, where A, how we determine what this matrix A is going to be, is you just take U to be the first column of this matrix, V is the second column of the matrix, and then W is the third column of our matrix. So again, you can interpret this matrix multiplication as a linear combination of x1 with 1, 0, 1, which is this part right here, and then x2 times the second column, plus x3 times third column. So this is the exact interpretation of matrix multiplication I was discussing earlier. So these two things coincide with one another. You should expect that they give you the exact same matrix at the end of the day. So this is how you can interpret it, or interpret linear combinations as matrix multiplication. Oh, so I guess just as an example, so this is saying if the components of X are the scalars in the linear combination, the vectors u, v, w form the columns of A. So this is really just what I was saying in the previous slide. And then the product A times X is computed via dot products between rows of A and X. So I guess I'll go through this quick computation. So you can interpret, like if you want to do the matrix multiplication of this 3 by 3 matrix with this 3 by 1 matrix, you can also write it as 1 times x1 plus 2 times x2 plus 1 times x3. So it's the dot product of this first row with this column here. And then you can do the exact same thing. So the second entry would be the dot product of the second row with this column. So that's going to be x2 plus x3. And then the dot product of the third row with this column is just going to be x1. And so you end up just getting the exact same thing I had in the previous slide. Right. So there's kind of like, I'm really just showing a bunch of different ways to compute these various products. I will say like the most common way of doing matrix multiplication is this way right here, where you do the dot product of the row with the column to determine the entries. Okay, and I think the next slide is just computing what I just did. So I write it out in more detail. So like 1, 2, 1 dotted with x1, x2, x3, so on and so forth. So you end up just getting this exact thing. So we see that A times X describes a linear combination of the columns of A. Okay, so there's like an example. How much time do we have left? Oh, I have 14 minutes. I can take all the time in the world. Okay, so this is, for this one, it wants you to compute the linear combination of 2 times U minus V plus 2 times W using matrix multiplication, where U, V, and W are exactly as they were in the previous slide. So if I wanted to do this, like I want to write things out in terms of A times X, like, of course you could just compute this linear combination pretty quickly, but it's defeating the purpose. Like we want to do this via matrix multiplication. It'll be useful later on. So in this scenario, can anyone tell me, like, what is our matrix A going to be? You don't have to read it off entry by entry, but what are the columns of A going to be? Yeah, go ahead. Yeah, it's the exact same matrix we had before. So our matrix A is just going to be made up by the columns. Like the first column is going to be U. V, the second column is V, so it's 2, 1, 0. And then W is 1, 1, 0. And then we're going to multiply this by some vector X. So what is X going to be if we want to be able to express this linear combination as a product of matrices? Yeah, so the first entry is going to be a 2. Then what's the second one? Yeah, -1. And then the third one, yeah, it's going to be 2. So the scalars you have here determine the entries of your vector x that we have. And then at this point in time, all you have to do is just multiply these matrices together, and you'll figure out what this linear combination is going to be. So this is going to be equal to 1 times 2. I'll do it in detail. Plus 2 times -1 plus 1 times 2. So that's the dot product of the first row with 2 minus 1, 2. Then you dot 0, 1, 1 with 2 minus 1, 2. So this is going to be 0 times 2 plus 1 times -1 plus 1 times 2. That's the second entry. And then the third entry is going to be 1, 0, 0 dotted with 2 minus 1, 2. So this is going to be 1 times 2 plus 0 times -1 plus 0 times 2. And so what does this end up being? So this is 2 plus -2 is 0 plus 2. So we get a 2 here. 0 times 2 is equal to 0 plus -1 plus 2 is equal to 1. And then we have 2 plus 0 is 2. So again, we end up getting a 3x1 matrix, which should make sense because at the end of the day, we're really just adding up scalar multiples of these 3x1 matrices. So you should get a 3x1 matrix at the end of the day. Any questions about this so far? Yeah, I don't know. Maybe this is like boring for some, but I mean, matrix multiplication is one of the most important things in this class. So if you don't understand matrix multiplication, it's going to come back to bite you pretty hard. So what we've seen so far, like the situation we've had so far is we're given what our matrix A is, and we're given X as well. And then we're multiplying those things together to get a new vector B. But the more interesting question is going to be what happens when we have A and we have B and we don't know what X is going to be. So to answer that question, like how you determine what X is going to be if you have what A and B are going to be, is we're going to have to introduce this idea of like, I was just going to say like invertible matrices. Like invertible matrices are going to show up here. So the main question is, how does one solve the equation AX is equal to B when we know A and B, but we don't know what X is equal to? And so we'll look through an example. Later on, we'll have a more sophisticated way of solving this via like Gaussian elimination and like matrix row reduction. But for now, we can just rely on basic algebra. So to begin, we're going to assume that our vector B is given by B1, B2, and B3. And so if we have AX is equal to B, this is equivalent to saying that we have X plus 2x2 plus x3 is equal to B1. X2 plus x3 is equal to B2. And then x1 is equal to B3. And I should specify we're using the same matrix A that we were looking at in the previous examples. So like we're assuming A is equal to this matrix right here. So like these equations, maybe I shouldn't talk so much, but this is like these x1 plus 2x2 plus x3, x2 plus x3, and then the x1. This equation, like this matrix we had here, that's where this equation, like these equations are coming from, right? And so we want to be able to determine what x1, x2, and x3 are in terms of B, like B1, B2, and B3. And so what we can do here is we're just going to use a lot of substitution pretty much, right? From the very beginning, we have that x1 is equal to B3. So that means we can substitute in x1 is equal to B3 and then subtract it over to the right-hand side to get that B1 minus B3 right here. And if you do that, you get a new system of linear equations. So if you substitute in x1 is equal to B3 and then subtract it over to the right-hand side of this first equation, you get 2x2 plus x3 is equal to b1 minus b3. And then x2 plus x3 is equal to b2. Okay, and then you can do something, I don't know if you've seen this in like high school or something, but you have a system of linear equations with two equations, and you want to determine what x2 is, and you want to determine what x3 is. One way of doing this is you can take 2 times x2 plus x3, and you can subtract from it this x2 plus x3 right here. If you do that, all that's going to be left is just an x2. So if you subtract this equation from, or if you subtract this equation by this equation, you're just going to end up getting x2 is equal to b1 minus b2 minus b3. So all we're doing is just subtracting. Like if you subtract these two linear equations with one another, you just get x2 is equal to b1 minus b2 minus b3. So that gives you x2 in terms of b. And then once you know what x1 and x2 are in terms of b, like you can just substitute in x2 is equal to b1 minus b2 minus b3, and then bring everything over to the right-hand side to determine what x3 is going to be. So because we have that x2 plus x3 is equal to b2, this implies that x3 is equal to b2 minus x2. So then you can just subtract everything over to the right-hand side after substituting in what we had before, and you would have that x3 is equal to 2b2 minus b1 plus b3. So that tells you what x1 is, or x1, x2, and x3 is in terms of the entries of our vector b. Does this make sense? Are there any questions about like what was done to determine what x1, x2, and x3 were? Okay, and this is kind of, maybe this isn't the best word, but it's like kind of like a primitive way of doing things. It's like what you did in high school. We're going to learn much more sophisticated means of determining what this stuff is going to end up being equal to. And so once you have that x1, x2, and x3 is expressed in terms of b1, b2, and b3 in the following ways, you can express this vector as a linear combination of vectors with weights b1, b2, and b3, right? So like b3 gives you this entry right here. We have b1 minus b1 gives you 1 minus 1 here. And then b2 minus b2, and then 2b2 gives you the minus 1 to 2 right here. And so it gives you this linear combination of column vectors, which we can then interpret as matrix multiplication. So you can really express all of this in terms of the following matrix product, right? Where this becomes the first column, this becomes the second column, and this becomes the third column. And so this matrix that we've determined by solving the system of linear equations is going to be called the inverse matrix of A. And we'll say more about like inverse matrices in chapter 2. But again, this is just like previewing why it's going to be important later on. So if you have such a matrix, the matrix A is going to be said to be invertible. And then we end up denoting the inverse matrix as this like A to the minus 1. So this matrix right here is our inverse matrix of A. Okay, and let's see what I maybe need to speed up a little bit. So an important notion or definition that's going to come up a lot in this class, and again, we'll talk about it more later on, is this notion of linear independence and linear dependence. And so what it means for something or a matrix to be linearly independent is if you consider the equation AX is equal to 0, like the column vectors of A are said to be linearly independent if this solution is going to be unique. So there's only one vector you can multiply by A to make it so you end up getting the 0 vector. And of course, that vector would end up being equal to 0, 0, 0. Like if you multiply any matrix by 0, 0, 0, like you're just going to get the 0 vector back. So if 0, 0, 0 is the only solution, it means that your column vectors are linearly independent. Let's see. There's an example. I'm going to skip this example. It's something you can look at later on. To conclude class, I just want to go through one final example. Because I talked about linear independence, we should see an example of something that's going to be linearly dependent. So if we consider these vectors u, v, and w, they can define a matrix like we've been doing thus far by making it so the first column is u, second is v, third is w. And so this question is asking you to determine whether or not A is going to end up being invertible or not. An equivalent question is asking if the columns of A are going to end up being linearly dependent. And we're pretty much out of time, so I'm just going to give you the answer, which isn't very fun. But the answer is going to end up being no. The reason why it's no is because if you do u minus v, it ends up being equal to w. So what this implies is that we have that 0 is equal to w minus u plus v. And so in terms of matrix multiplication, so like w is equal to u minus v, which implies that u minus v minus w is equal to 0. So if you express this linear combination in terms of matrix multiplication, you're going to get the following matrix product. So you have your original matrix A multiplied by 1 minus 1 minus 1, i.e. the coefficients of these vectors, ends up being equal to 0. So you see that you can multiply this matrix by something that's non-zero, and you end up getting the 0 vector back out. So this means that the equation ax times 0 has two solutions. It has this solution here, the 0, 0, 0 vector, but then it also has this solution here. So this implies that A is not going to be invertible, which then means that these vectors are not linearly independent, they're linearly dependent. So this is something we'll talk about in more detail later on. Again, this is kind of just like a preview to to develop intuition. So I kind of rushed at the end. Are there any questions about anything we discussed today? Okay, if you have any questions about the homework over the next few days or over the weekend, you can email me. And we'll talk about it a little bit in class on Monday.